Superposition theorem in a scalar network. In a circuit, a linear relationship, also known as linearity, describes a consistent and proportional relationship between voltage and current. This means that when voltage changes, the current changes proportionally, and vice versa. This relationship is fundamental in many circuit components and analysis methods. The superposition paradox in a scalar network isn't a standard term with a universally accepted definition. However, it can refer to situations where the superposition principle, commonly used in linear systems analysis, leads to seemingly paradoxical results, especially when dealing with quantum mechanics or complex networks. The core idea is that while the superposition principle, where the response of a linear system to multiple inputs is the sum of responses to individual inputs, is mathematically sound, its application to certain systems, particularly those involving quantum phenomena or complex interactions, can lead to counterintuitive or paradoxical outcomes. In essence, the superposition paradox in scalar networks or in any context highlights the limitations of applying the superposition principle when dealing with systems that exhibit nonlinear behavior, quantum effects, or complex interactions. It underscores the challenges in understanding how quantum systems behave, particularly when measurement or observation is involved. In this experimental study, we employ the conventional configuration of the scalar network. Through extensive theoretical analysis and empirical testing across multiple scenarios, we identify an operating regime in which voltage and current do not conform to the superposition principle characteristic of linear systems. Notably, the voltage measured across the bridge rectifier increases, while the input power delivered to the system approaches zero at the microwatts level.
Going briefly over the setup, you have seen this setup before. We have the transmitting side over here. We are measuring voltage on the input side. We have the receiving side in here. We measure voltage on the output side via the bridge rectifier. We have the DMM connected to the bridge rectifier and measure the voltage we receiving or we are generating via the output into this load. The frequency is 1.112 megahertz and we have 4.59 volt we're using as the voltage to our amplifier into our transmitter. So I will energize us now, and it will take a couple of seconds for the system to adjust, which is an interesting phenomenon. Normally it happens instantaneously, but that is currently not the case. So what we can see here is we have about 320 milliwatt power delivered to the load, the bridge rectifier. We measure 44.35 volt on the DC side, output side from the bridge rectifier. We have 1.5 volt, the yellow line is the input side from the oscilloscope, and we have the green line, which is the output voltage going into the bridge rectifier. We measure 20 volt, so 20 volt, yes, it produces for us with a current around 44 volt. That seems to be correct. However, currently the only load is the capacitor, there is not much more load. So if I now change in this configuration now the system, and we have zero current on the input side. So what also changes is the green line of on oscilloscope, which is the output side. On BSC also we have 74 volt, we have almost twice as much. Now we have twice as much voltage now generated on the output side. However, we have no current. So we can see on oscilloscope that current blue line and green line is more aligned, while the voltage on the input side is much lower. So how can we explain this phenomenon? So if you look at impedance matching, that cannot be the explanation. Impedance matching would be that we apply an impedance network, either an active or a passive one, from the amplifier to the load, where we apply that the load impedance currently at a couple of kilo ohm would then be applied to the source power in order to deliver the power we require. But that would also mean at 4.5 volt we would presume probably close to 1 ampere would go in at that level if we would do impedance matching. That is not the case. Another contender would be, well, if you have the wrong polarity, or if I have opposite polarities of current and voltage, they should actually cancel each other out. Well, that's not the case either, because otherwise then I would not see current here higher up on the system, providing me with this alignment that would be going close to zero. That would be the logical explanation for what we are seeing here currently on the power supply. If I stop that for a second, that is currently how it looks like in the aligned fashion. Let me take that out for a second. So we are back to our 75 milliwatt power consumption. If I stop that on oscilloscope, that's how it looks on oscilloscope if it's not aligned, or if there's not a superposition in a non-linear system. Superposition normally applies only to linear system, but here it's a non-linear system where quantum effects are taking place, which are hard to define. So if you want to replicate this kind of scenario, you would probably try a solenoid coil, and you would try a pancake coil. However, I have done that and it does not work, because the current has to come from somewhere. And the difference between other normal solenoid coil and normal pancake coil is here. These are torsion field generators which have a magnetic component. So my guess is here, and that needs to be confirmed by others, is the magnetic field here is aligned in the system in this kind of configuration that it actually entangles with the voltage and allows for voltage and current to be applied in the same fashion. It's technically a base holder. However, that is my theory. It needs to be confirmed by others. However, as you can see on a power supply, we have zero power consumption, and we have twice as much output on the bridge rectifier for a slightly higher power provision to the system. So I encourage everybody to replicate that. However, if you need advice or some other information, you can contact me as a member on my website. And I thank you all very much for watching. Until next time. Goodbye.